Okay, so this is where we left off. This is a cartoon showing joints, folds, and a fault. So let me just point out the difference here. Joints, breaks in the Earth's crust, uh, faults, breaks in the Earth's crust, but there's no displacement here between the sides of the joints. Here, the rocks have been displaced from each other. So the rocks have been stressed past their elastic limit and they've broken. Brittle rocks will do that. These rocks were ductile. They've been folded. The force at work is compression, squeezing. And the force at work here, oops, yeah, that's right. The force at work here is tension. So we'll talk about how those all form. All right, so these are joints. We have previously talked about columnar basalt and how, I can't draw straight, and how basalt, when it solidifies, has this characteristic of having these weak areas that are polygonal in shape. So when they're weathered, Mother Nature, when they're subjected to rain, to weather, everything is concentrated in those weak areas. So we end up with this weathering that's taking place along these jointing patterns. So joints can give us some really, 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 really cool landscapes out there. This, on the other hand, is a fold. We see a series of folds here. Here's the up fold, and here's the down fold. And these are kind of V-shaped folds. They're not open folds like this. So that means that the compression was even stronger to fold them into these V-shapes. Sometimes these are referred to as chevron folds. And then this is a fault here. Notice the displacement. The rocks have been cracked. I need a different color. The rocks have been cracked and there's been movement. Can you see what's happened here? This has dropped down. This chunk of rock has dropped down in relation to these other rocks. So that is a normal fault, and we'll talk about how to recognize these in a second. Let's talk about strike and dip first, though. Strike and dip are two very important measurements for determining let me be able to talk here, for determining the way that rocks are oriented in the field. And you might think, who cares about that? Well, a lot of people care about that. Engineers care about it. Construction people care about it. Structural geologists, the ones that go out and do this mapping, these folks are crazy. They can stay out in the field for months at a time mapping rocks. So strike and dip. Strike is the compass direction that the rock strata trends. So it's going to be, we're going to say north, south, northeast, northwest, whatever the compass direction is. The dip is how the inclination or the tilt of the bedrock. And it has two measurements to it. We want to know what the angle of the dip is, but we also want to know what direction it's dipping. So a Brunton compass, that used to be the tool that every geologist worth their salt had. The Brunton compass was used because it was metal, it was sturdy, it has a level on it, so you can determine what the angle of the dip is, and of course the compass is going to show you the direction. So this probably has been more confusing to geology students than anything. It's probably one of the reasons that folks flunk out of structural geology, being able to determine strike and dip. But I'm going to give you a quick and easy way to do it. Dip is what we should measure first. And if we measure dip, strike is always 90 degrees from the dip. Okay, so it's perpendicular to the dip. Now I'm going to get my little pen here and see what kind of a botched up job I can do drawing this. Yeah, I want it to be down here though. So on a geology map, you would see something like that, a symbol like that. That's the strike and dip symbol. The long line represents the strike, how the rock is trending in the field, and the I needed a different color here. It's probably having a hard time seeing that. And then this little tick mark right here, that is the dip of the bedrock. And then there will be a number on this. It might be 30 degrees, but that would tell me that that's not 300, that's supposed to be 30 degrees. That would tell me that the rock is tilting 30 degrees to basically the north, a little bit west of north. But that's what those symbols show. Again, they're always perpendicular to each other. So it might be like this, that way. It could be like that, be that way. So any variety of ways, but the long line is the strike line, the short line is the dip line. Here's an example. These rocks here here's the strike of the bedrock. The strike is this way, strike line, and then the rocks are dipping this way. They're dipping to the southeast, and we have what the dip angle is. No, we don't have a dip angle on it. But the Brunton compass, we would lay the Brunton compass on the rock, and that would tell us what the angle, the level would tell us what the angle is. And then the directional component of the compass tells us what direction the rocks are dipping in the field. So on a geology map, this is what that would look like. Different rocks show up with different symbols on a geology map. Limestone shows up in this brick-like pattern because that's the jointing pattern in limestone. It tends to weather into these nice regular brick shapes. Sandstone is shown on a geology map with little round dots to represent sand grains. Shale is shown, it's hard to see that here, but shale is shown on a map like this, with little dashed lines representing those platy shapes of the clay particles. So that's dark color there prevents you from seeing the dashes, but when you see something like that, you know that it is that's the code for shale, S-H-A-L-E. And then little cross marks like this, sometimes you might see little marks like that. That's for crystalline rocks, and that's either a granite or it could be a metamorphic rock like gneiss. So those are the codes that you see on the map. Then maps are always oriented toward the north, so you have a north arrow here. There's the north arrow. And then this says, hey, those rocks are dipping 40 degrees toward the southeast. North, here's southeast, this direction, so toward the southeast. These rocks would be dipping 40 degrees toward the southeast, and the strike of the bedrock is here. Oops, I'm in the wrong one, that direction. So the codes on a geology map will indicate the age, what type of rock it is, and of course we see the structures. Folds would be shown also, folds and faults would be shown also on a geology map. So the strike, let me just go to this one right here. This is the right hand rule. If the fingers of your right hand point down dip, then your thumb points in the direction of the strike. If you ignore that rule, then you might misinterpret the strike of the rock. So put your right hand on the rock, down dip, and your thumb will point in the direction of the strike. Now, how to go about figuring out what the strike is? Well, let's figure out what the dip is first. And one way to do that is with water. Have a bottle of water and pour water on the rock. The water is going to flow down dip. And you might need to do it in several places. Then you can take the average of the areas And once you have the dip direction, strike will always be 90 degrees from that. So this example is pretty easy right here. Here's the geologist pouring water down this rock that's sloping down toward the water line. So the water is going to flow this direction. So that's going to be the dip of the bedrock. And then the water line itself is actually the strike of the bedrock. If you use that right hand rule, the thumb would be pointing in the direction of the strike. That's probably more than you'll ever need to know, but if you're taking a lab, then I'm sure that your instructor will have some exercises to do where you're calculating the strike and dip. Well, why do we need that? Well, we need this because we're talking about movements along the strike of the bedrock, that horizontal movement where we would have a strike-slip fault, and we have movements along the dip of the bedrock, the vertical plane. We'll have movement in the vertical plane, and if we have movement in the vertical plane, we have a dip-slip fault. So this is a dip-slip fault. What has happened here? This chunk of rock has dropped down in relation to this chunk of rock. Strike-slip faults would be if we had this moving this direction or this one moving this direction and just in a different speed, or moving back this direction. We'll see how it depends on what direction the other block is moving as to what type of strike-slip fault we call it. So let's look at dip-slip faults first. These are called normal. Some of them, one type of them is called a normal fault. A normal fault is caused from tensional stresses. So every type of fault that we have across Nevada, the type of fault that we find in Iceland, the Rift Valley of Africa, the mid-ocean ridges, those are all normal faults because the one chunk of rock is dropping down in relation to the other chunk of rock. So the block of rock above the fault surface is called the hanging wall. If the hanging wall moves down in relation to the footwall, we have a normal fault. So if the hanging wall moves up in relation to the footwall, it's a reverse fault. And if the hanging wall is thrust completely over the footwall, it's called a thrust fault. So reverse and thrust faults are both caused from compressive forces, from compressive stresses. A thrust fault is just a low angle reverse fault. And if you're wondering where those terms hanging wall and footwall come from, I'm going to tell you that in a minute. A strike-slip fault results from shear stress, and there are two types of strike-slip faults. There's a left lateral strike-slip fault, and there's a right lateral strike-slip fault. Those terms, hanging wall and footwall, those are old mining terms. Back in the day, when miners had to use lanterns before there was electricity in mines, they would, if it was a normal fault, they would have their lantern on the hanging wall and the miner's feet would be on the footwall. And usually what they were mining, for example, gold, gold would precipitate out along weak areas in the crust. Well, where's a weak area in the crust? Along a fault line. So you have water that's carrying gold and quartz, and as that water flows along, the gold and the quartz precipitates out. When a miner would find a vein of quartz and gold, then they would just follow that vein, and it was usually along a fault line that they were following it. So hanging wall, footwall, lantern on the hanging wall, feet on the footwall. Now, this is a normal fault. How do I determine whether it's a normal fault? Now, you got to follow along with me. First of all, you find the break. The break is easy to find in these block diagrams because it's where, sorry, this keeps jumping. Because it's where the dark line is showing the break. So then we find the break and the block of rock above the break. And if we're looking at this line, then this is the rock, the way the line is oriented. This is the block above the break, and that is the hanging wall. So what did the hanging wall do? It moved down. If the hanging wall moves down, that is a normal fault caused by tensional forces. This is called a normal fault because if crust is being pulled apart, then under the influence of gravity, what's going to happen normally is that the hanging wall, one of these things is going to drop down. The hanging wall will drop down. So, normal fault. How do we find these things in the field? Sorry, I keep touching the mouse and it keeps jumping around. This area of displacement right here is called a fault scarp. That is short for escarpment, E-S-C-A-R-P-M-E-N-T. Escarpment is just a fancy word for like a vertical cliff, escarpment. So just to shorten it up, that's the fault scarp. And especially when these are fresh, you know that there's been movement throughout time. They can get weathered and eroded away, and it becomes a little bit more difficult to detect these out in the field, so you might have to have another way to determine that faulting has occurred. Normal fault again. Find the break. Here's the break right there. The chunk of rock above the break, look at the orientation of the line. The chunk of rock above the break is the hanging wall. What did the hanging wall do? It moved down, so that is a normal fault. Tensional forces. How does that look like what does that look like in the real world? Well, this is in the Basin and Range. This is in California, but it's the part of the Basin and Range that is in California. This is the hanging wall down here. This area is called Surprise Valley. So the valley itself is the hanging wall. The hanging wall. The mountain range is the footwall. The rocks in this mountain range, which you can't see right now because they're kind of snow covered, but the rock layers up here are about 5,000 feet or more below here. Every time there's an earthquake, then this gets pushed up a little bit, this drops down more. And there's the scarp. There's the fault trace right here. So all of Nevada is just a series of normal faults. All the Basin and Range is just a series of normal faults where the crust is being stretched apart and the hanging wall drops down below the footwall. That is the very definition of a normal fault. So what's the word I'm looking for? The description, that wasn't the word I was looking for, but it'll do. The description of this type of topography when we see it actually comes from the Germans. The Germans were big into geomorphology, going out, mapping all of these different landscapes on Earth's surface. And if they were doing the work, then they got the privilege of naming these structures. So they called this type of feature where you have these fault block mountains, they called them Horstengraben. The Horst, in German, that word means thicket, T-H-I-C-K-E-T. And when you think about it, when you look at Nevada, if you're driving across Nevada, you don't see a lot of vegetation. You see a lot of sagebrush and that kind of thing at the surface. Where do you look to see any trees? You look up at the top of the mountain where the thicket is. So that was called the Horst. And then the down drop block was called the Graben. So that's Horst and Graben all across the Basin and Range. Horst is the footwall, Graben is the hanging wall. Tensional stresses at work. And this is what it looks like. These mountains are weathering away, and they're actually burying themselves. Here's a little bit of weathering and erosion and mass wasting going on. So to get these little isolated they look like islands out here. In fact, that's what that word right there means. Inselberg is island rock. So these mountains are burying themselves in their own waste. There's another view of Horstengraben, normal faulting, Basin and Range, Basin and Range. The mountain ranges are the footwall, the basins are the hanging walls. And then here's a good example of a scarp. That happened, that movement happened, I think it was the 1960s. There was a big earthquake in Nevada called the Fairview earthquake. And this is when that chunk of earth dropped down in relation to this. This used to be connected up here, but it faulted. Again, those stretching, those tensional forces at work. All right, what about a reverse fault? In a reverse fault, the hanging wall has been squeezed up over the footwall. So there's the break. What do? First thing we do is find the break, and then we identify the rock, the crust above the break as the hanging wall. And then we look to see what the hanging wall did. The hanging wall has been moved up in relation to the footwall. That's a reverse fault from compressional forces. Sometimes in rocks, if you have the right color, sometimes you'll see the mark of Zorro. If you ever see the mark of Zorro in rocks, that indicates that that's a reverse fault. Here is the break, right through here. Sorry, I'm waving the line when I shouldn't be, but right through here is the break. And hanging wall is going to be up here. Hanging wall, footwall down here. What did the hanging wall do? It moved up. So that is a reverse fault. Okay, so what's the difference between a reverse and a thrust fault? Well, that's a reverse fault, compressional stress. This is a thrust fault. Again, compressional stresses at work. It's just that the hanging wall has been thrust completely over. So a thrust fault is just a low angle reverse fault. Still, both of them the same. The hanging wall still is moved up, and the stresses are still the same. And the movement, again, these are dip slip faults. The movement is along the dip of the bedrock. This is another thrust fault. There's the hanging wall. There's the break. Right there's the break, sorry. There's the break. Here's the hanging wall, the chunk above the break. What did the hanging wall do? It has moved up, so that is a sorry, my Confer Zoom just kicked out on me there, so I don't know how much of that you all got. But this is the hanging wall here. The hanging wall has been thrust completely over the footwall, so a thrust fault. And then this is Chief Mountain in Montana. This is a fairly famous thrust fault. Here is this darker color rock up here at the top, matches this rock over here. So all that rock has been thrust completely over this rock here. It's just that this stuff over here in the middle has been weathered away. So that's a slice, that's a remnant of this layer of rock that's right at the top of Chief Mountain. So that is a thrust fault. And then that brings us to strike slip faults. I don't know why that says strike slip faults. It's just one strike slip faults. The movement along a strike slip fault is along the strike of the bedrock, that horizontal plane. Remember, if this thing was moving this way in the vertical plane, then it would be a dip slip fault. But it's moving horizontally, so it's a strike slip fault. And they come in two types, right lateral strike slip fault and left lateral strike slip fault. So this is analogous to Point Reyes. There's the famous fence at Point Reyes. This would be the Pacific Plate here. Let's just put PP, the Pacific Plate. This is the North America Plate here. And we see that the Pacific Plate is moving off toward the northwest. So you've got to use your imagination here to figure out what this is. So let's say that you are standing here on the Pacific Plate and there's an earthquake and the fence, it was connected at that point. So there's an earthquake, you look over and you see that the other part of that fence has moved this direction. And if you're facing the North America Plate, that means that the fence has moved to your right. Okay, think about that for a second. Pretend you're standing on the Pacific Plate, there's an earthquake, the fence moves. You look across to the North America Plate and the fence has moved to your right. Okay, now if you're on the North America Plate over here, there's an earthquake, you look across at the Pacific Plate and that fence has also moved to the right. So no matter which side of the fault line you're on, it looks like the other side has moved to the right. If that's the case, that's a right lateral strike slip fault. So the San Andreas Fault, yes, it's a transform plate boundary, but it is a right lateral strike slip fault. Yes? Now, what about this little cartoon version right here? This is a left lateral strike slip fault. So if we're standing over here and there's an earthquake, we see this road on the other side has moved to our left. But if we're standing over here and we look over at the other side, we're facing this plate, we look to the other side, it has also moved to the left. So that would be a left lateral strike slip fault. But our San Andreas Fault and all the other faults associated with it, they're right lateral strike slip faults. This is offset stream along the San Andreas Fault. Everything is being moved off this direction. So on this side of the fault. So we have streams, we have ridges that shudder past each other as they're being moved either from an earthquake or just creeping motion. And you see this is a famous creek. You can walk, there's a, like a, I don't know if it's not a national park, but at least it's a county park or something. They have a little walking trail that you can walk along and see how this has taken place. So that creek has like a dog leg in it, a bend in it here, as the other part of the creek is being shifted to the northwest. And the entire Point Reyes Peninsula, if we had had our field trip, we could have gone to this exotic piece of land because it doesn't match anything that's over on this side of the fault, because all this land right here has hitched a ride along the San Andreas Fault and it's moved to the north. So the rocks are totally different than any of the rocks over here. Stranger in a strange land. This is in Hayward. When they built this curb, they didn't build it with the offset like this. This is just creeping along. So now we have this offset. And this shows, this is about a year, somebody drew an arrow when it was connected. That's probably about a year's worth of movement there. You can imagine that any home or any road that's built along this, it's going to be a constant battle. If it's your house, your cabinets aren't going to shut properly. It's drainage pipes can break because of this gradual shifting. And then this is an orange grove. And you can see the shifting of the orange grove. Again, that is a strike slip movement in the horizontal plane. This is a 6-foot movement that happened in 20 seconds on a fault line in Japan. So what type of fault is it? Well, if you're standing over here, it looks like the other side moved to your right. So that's a right lateral. And if you're standing over here, it looks like that side moved to your right. So that's also a right lateral strike slip fault. There's another view of it. So here we are, normal fault, hanging wall has moved down in relation to the footwall. Reverse fault, the hanging wall has moved up in relation to the footwall. So if you are standing here on the footwall, then the hanging wall would be hanging above your head. If the hanging wall is above your head, then that's a reverse fault. Then this is a thrust fault, hanging wall thrust over the footwall. Here's a left lateral strike slip fault, and here's a right lateral strike slip fault. Hopefully you know the differences between these now. I will have a worksheet that I will post later for you to work through, and it will be graded. So let me know if you have any questions on how to determine the difference between all of these faults. And I will pick up with joints the next time we meet. See you later.